Hello everyone, here's another Physics IB past paper review. This one is from May 2018, standard level paper 2, and this is the last question, question 6. Here we have a radioactive nuclide, beryllium-10, undergoing a beta minus decay to form stable boron nuclide. Our first task here is just to identify the missing information on this nuclear reaction. Now, here we can see the beryllium-10, turning into or transmutating into boron. There's the beta minus, and there's our anti-neutrino, so all is looking good. What we need to just add on is a couple of things. The question tells us that it's beta minus, so I'm just going to go ahead and put on a little -1 sign. Actually, I'll do that a bit nicer. -1. And the reason we want to do that is because when we're balancing or when we're adding information to our nuclear reaction equations, we're going to need to keep in mind two things. First of all is conservation of charge down the bottom, and then the second thing is conservation of nucleons or nucleon numbers. We'll just say nucleons. So the number of nucleons has to stay the same, and the charge has to stay the same from the beginning to the end. So whatever's on the before, that's before, this is after. We can't have charge just appearing or disappearing, and we can't have nucleons appearing or disappearing. So let's go ahead and take a look at the nucleons first of all. So we need to keep track of them. There's to begin with, there's 10, and then so here you can see there's 10. It's beryllium-10. That means there's 10 neutrons and protons together. As we move through, the beta minus obviously has no nucleonic number. There's no protons and neutrons associated with the beta particle, and the same goes for the anti-neutrino. There's no proton and neutron number associated with it. So therefore 10 has to be conserved. So this is quite straightforward. This is going to be boron 10. Okay, there are 10 protons and neutrons associated with this boron here. Okay, now we can do the conservation of charge down the bottom. Again, we need to keep track of the before and after. Well, in this case, we don't know the before, so let's keep track of the after. We have a 5. That means there's a charge of 5 elementary charges associated with the boron. That's clearly telling me, hopefully you can recall, it's telling me that there are 5 protons. It's a positive 5 value, so there is a plus 5 elementary charges, and that's those 5 protons. And then the beta minus is a negative elementary charge. So 5 minus 1, of course, is equal to 4. So there's a net charge on the equation afterwards of 4. And that means that we have to have 4 to begin with, because we've said that we cannot have charges just appearing and disappearing. So that must mean that there are 4 protons associated with the beryllium-10. Okay, so part B, we have a half-life graph, and it's still referring to our beryllium-10 sample. This time it's saying that we have an initial number, which is given as an N0 right here. This is the initial amount, so we can call that 100% of the initial sample. And then this graph is showing how that number decreases in terms of the half-life. So you can see it dropping down like this in terms of the amount of that original parent material. So here we would have 75% of the parent material. This is the first half-life right here, and then 25% and all the way down. So just to put a few key markers on here. Let's go ahead and just roughly put this in at about here. This is the half-life. So whatever time this is 1 half-life. And that means then the next half-life is going to be, so this is, let's just see if I can draw this on. This is the first half-life. Half of 50% is 25%. So this point on the graph, this is going to be 2 half-lives. Okay, so the question is here, how does the daughter material relate to the parent material? So assuming that the daughter material, in this case boron 10, doesn't decay any further, let's just say that it's stable, then clearly at the beginning there's going to be none of it. So at the start there will be 0. So it starts from 0, 0. So at the very beginning there's 100% beryllium, 0% boron. And then clearly at the half-life point, the first half-life, if half of the beryllium-10 parent material is still remaining, that must mean that it would have turned into boron. And so these values have to be the same. And really what we're saying here is that these graphs should mirror each other. So this would be curving upwards and then continue up to here. In fact, we can see exactly where it would be because this end point on our graph is just past the, let's say it's at the 20%, so that would mean 80% boron. So let's just make sure that we can indicate that on here at the very end. We'll put that as a point. So it's ending, the end line is going to be around about 0.8 n noughts to correspond with the, if we were to put this on here, this would be 0.20 n noughts, which means this one has to be 0.8 n noughts. And we would also say that it intersects at the 0.5 n naught at the half-life, that first half-life. All right, so for part 2, we're given a time frame. So we're told that after 4.3 times 10 to the 6 years, there's a ratio between the number of produced boron nuclei and the number of remaining beryllium nuclei. So remember that the beryllium is the parent and it's going to decay down to boron. So the number of produced boron is the number of daughter material that would be at this time. So that's going to be the original amount of beryllium minus the new amount of beryllium. Okay, so the difference between the original and the new amount of beryllium is going to be the boron. Okay, we saw that with the half-life graph. And that's going to be over the number of remaining beryllium, which is n. The time value here, this is my time. That's the time elapsed. And then I have to prove, I'm given the answer, but I just have to prove it. I'm given the half-life here. Okay, so let's first of all look at the ratio between the time elapsed and the half-life. This is often the exponent n value, if you've come across this equation before, which you may or may not have. N is equal to n naught, and then the half-life to the exponent n, and then n is the time elapsed over the half-life time. So this n value is going to be the time elapsed, which we have as 4.3 times 10 to the 6 years, over, let's just do that again, over, and my half-life time here is 1.4 times 10 to the 6 years. So this gives me an n exponent ratio of 3. So this should tell me that I've had 3 half-lives elapsed. The ratio between the time elapsed and the half-life is giving me this integer number of 3, and at standard level you won't have to do anything that's not a straight integer. So we know that 3 half-lives have elapsed. How can we prove that? Well, we're going to use our ratio here that we've just figured out. So what does that look like? Well, let's just move this out of the way here. I'll just leave that 3 because we know that we're searching for proof that our half-life is 3. That's what we're going to try and prove. So recall that these n naughts and n's represent the original number of beryllium minus the remaining. So think about if you did a test and you got a score of 21 out of 25. This would be pretty easy to convert into a percentage, right? Well, same thing for our n naughts and n's. What we're looking for is we're trying to get a ratio of our original, in other words, what the exam is out of, the total amount that it's out of. This would be the 100%, and then the remaining score, or the remaining number of nuclei. So if I can rearrange this statement into an n over n naught, I'm going to get a percentage. And once I get a percentage, I can link it back to the number of half-lives, because remember, if I'm at 50%, I'm going to have 1 half-life. If I'm at 25%, I'm going to have 2 half-lives. And if I'm looking for, well, in this case, I'm looking for 3. 3 is going to give me, well, what I'm really looking for is the 12%, 12.5%. So if I'm scoring my test, I'm looking to get, in this one, I'm looking to prove that I've got 12.5%, because that would be 3 half-lives. So let's go ahead and do it. We're going to say that 7 is equal to n naught minus n over n. So 7n is n naught minus n, which means 8n is equal to n naught, which means, well, let's just go ahead. We'll go 1 over 8 is equal to n over n naught. Hopefully you can see those steps. And this is going to give me my decimal value, my 0.125. That, hopefully you can see, that's our 12.5%. So I can say, therefore, 3 half-lives. 3 half-lives have elapsed, and I've proven that this time is the half-life of beryllium. Okay, so last part of the question, part 3. This is really just a plug and play. We're still on our beryllium to boron transmutation. This time we've got some numbers. So let's recall our formula that we want to be using for these half-lives. We know that the new amount of whatever it is that's transmuted is going to be equal to the original amount multiplied by the half to the exponent n, where n is the time that's elapsed over the half-life time. Okay, so what do we have? Let's have a look at the question. It's used, beryllium-10 is used to investigate ice samples from Antarctica. Sample of ice initially contains, so this is our original, there it is, it's a number of atoms. So the n naught is, actually I'll just put it on here. This is the n naught in red. That's the original number of atoms. We need to state the number of remaining beryllium-10 nuclei or atoms in the sample after 2.8 times 10 to the 6 years. So this value here, this is the time that's elapsed. So this is my time. And in the previous question, we were given the half-life. So my n exponent is going to be time, which is 2.8 times 10 to the 6 years. Let's go ahead and call it annums, over the half-life, which from the previous question we know to be 1.43 times 10 to the 6 annums. So there's my exponent. Now all I have to do is plug in the rest of it. How much is left? So what I'm doing here is I'm looking for n. That's what I'm trying to find. And so I know that n is the original amount, which is my 7.6 times 10 to the 11. That's the number of atoms, or the number of nuclei that would be in that original sample, multiplied by the half, 0.5, to the exponent n. What's my exponent n? Well, this will tell me the number of half-lives. If you plug this into your calculator, you're going to get 2. So 2 half-lives have elapsed. So I can say that my, let's just do this, get rid of that. I can say that this is to the exponent. Oops, I just did the same thing. What I really wanted to do was put 2. There it is. We're plugging and playing. So the amount of beryllium-10 nuclei after 2.8 times 10 to the 6 years is going to be 1.9. I've gone to 2 sig digs because there's my 2 there. That's the precision that I can use. So 1.9 times 10 to the 11. And this would be atoms or nuclei. Okay, so we're into part C of this epic question 6. This ice sample that has the beryllium transmuting to boron being used to date the ice is moved. It's been taken to a laboratory for analysis. We know the temperature of the sample to be minus 20 degrees Celsius. First up, we're asked to state just a definition here. What is actually meant when we say thermal radiation? What is going on? And you'll remember from thermal physics we talked about what it is to have what temperature is, what heat is. In this case, the key to look out for is this thermal, and then that word there, radiation. So hopefully this is just a knowledge piece that you have. What is meant by thermal radiation? Well, this is a type of light. Certain animals use thermal radiation to see. Unfortunately, humans, we don't have that natural ability. We can use technology to help us. But of course, what we're talking about here is it's really electromagnetic radiation. And the region of the electromagnetic spectrum we're talking about here is EMR in the, you got it, infrared. Easy. All right, part 2 is a little more involved. We're going to be using some values eventually here from our data sheet, so just keep that in the back of your mind. But the question is asking, discuss how the frequency of the radiation emitted by a black body can be used to estimate the temperature of the body. So, recall that black body radiation looks something like this. And best example of black body radiation is the sun. If we looked at the light from the sun and we analyzed it in terms of intensity on the y-axis, which might be watts over meters cubed or meters squared, it doesn't really matter. And then on the x-axis, let's just say for now that there's wavelengths, and that would be in nanometers. What you typically see, and you'll be familiar with this shape, blackbody radiation, is you get this, oops, not a very good drawing. Let's do that again. You get the graph going up and then down. Again, actually, that's not very good. Let's try it like this. Something like that. You get the idea. And there's a peak. And this peak changes. It's at different colors or different wavelengths of light are in here. So I'm just going to put in blue and red just for fun. Blue and red there. So inside there would be the visible light. And what's interesting about this is there's going to be a peak. This is the peak wavelength. Wavelength peak right there. And this wavelength, this peak wavelength will shift. So the color or the EMR, the range of the EMR, the wavelength of the EMR at the peak will shift depending on the temperature of the black body emitting that radiation. And that is given to us by this ratio here. So the peak, or I should have said the wavelength max, is this constant number divided by the temperature. This is called Wien's law, or Wien's law. And really what it says is that the wavelength peak, I've said peak, I'll just keep calling it peak, or you could call it max, is basically proportional to 1 over the temperature. Okay, so remember that frequency and wavelength are linked by considering the photons. We would know that the energy of a photon is equal to hf, and we know that the that's also the same as saying hc upon lambda. So if we look at the relationship between frequency and wavelength, they're sort of inversely related. So if we've said that the wavelength is proportional to 1 over the temperature, we can say that the frequency is proportional to the temperature. Okay, so essentially as the temperature goes up, the frequency is going to go up as well as the frequency associated with the peak wavelength, I should say. Basically, it means that when something is, we can use this expression, you probably come across it, when something is white hot, it's going to be hotter than something that is glowing red. Okay, so think about it for a second. If it's glowing red, it means the peak wavelength is further along this way, more into the red, the longer wavelengths, which would be the smaller frequencies. And if it's white hot, that means it's this is going to be further up away from the red. It's going to be hotter. So as the temperature goes up, the frequency goes up as well. Or in other words, you could look at it as wavelengths. As the temperature goes up, the wavelength goes down. So temperature going up means this peak is going to go down the wavelengths. It's moving smaller numbers along the x-axis. Okay, so now we're asked to actually calculate that peak wavelength. So remember this is the, oops, didn't want to do that. I wanted to do this. This is our relationship, which is called Wien's law, or Wien's, I'm never sure how to say it, Wien's law. And so pretty straightforward. We're told the temperature at the beginning of the question, we were told that it was negative 20. So the temperature in Kelvin is, well, Kelvin is 273.15. Oops, 273.1. There we go, 5. And now I have to take away the 20 degrees Celsius. So my Kelvin temperature is 253.15. That's my Kelvin temperature. So that's Kelvin. That's my T. And my equation is over here. My constant, 2.90 times 10 to the negative 3. So the maximum or the peak wavelength is, well, let's plug it in. 2.9 times 10 to the negative 3 divided by this temperature in Kelvin, and that's going to give me 1.15 times 10 to the negative 5. And let's just pay attention quickly to my significant digits. Oh, I need 2 because I had 20 degrees. So actually, this is wrong. I'm going to go back and look at my calculator. I actually wanted 1.1 because I rounded up that 5. So you check your calculators. 1.1, there's my 2 sig digs, times 10 to the negative 5. So close to the end of the test. This is the very last step of question 6C. This is part 4. All we have to do is to derive the units of intensity in terms of fundamental SI units. Well, a couple of different versions of intensity. We saw on Wien's displacement law there that's common to use power density, which is kind of an intensity, and that would be watts or power over a volume. But I think it's more common to talk about intensity as a surface area. So if you think about the sun's energy coming down or the photons raining down, and we want to know the energy per second, the rate of energy hitting a surface of the earth or a surface of a solar panel or whatever it is that you're looking at. So the energy per second over the surface area. Okay, so in other words, That's power. That's power per meters squared. Okay, so let's look at the SI units. So we're going to call this intensity. Intensity is power per meter square. And of course, power is energy per second. And energy is in joules. So let's put it in joules per second per meters squared. Well, what's a joule? Well, if you're just not sure about what a joule is, think back to potential gravitational energy. So gravitational energy is mgh, and so we've got mass, gravity, height. So let's just put in our, so kilograms times 9.8, yeah, of course, the acceleration of gravity, so that's meters per second squared. And then height is meters again. And then we're going to be over seconds. So I'm just going to go, rather than making it more complicated, I'm just going to make that to the power 3. And just to make it less confusing, I'm going to make this meters squared over seconds cubed. And then this whole thing, this energy per second, this is my power. This can now go over my meters squared. So just one last thing to do. Of course, you can see that this meter squared is going to cancel out with this meters squared here. And we're going to get our fundamental units, which is going to be kilograms over seconds cubed. Oops, that's a bad S. Seconds cubed. And so in IB, that's going to be kg, so kilograms seconds to the -3.